Ancient seafarers, with no maps or compasses as we know them, pinpointed tiny islands thousands of miles away across the vast empty ocean, guided by invisible clues in the waves and stars. A mysterious map from 1513, drawn by an Ottoman admiral, appears to show a coastline strikingly similar to Antarctica, centuries before its official discovery, and perhaps even free of its immense ice sheet. Viking legends speak of magical sunstones that could find the sun's position even when it was completely hidden by thick fog or clouds, a feat modern science suggests is possible with certain crystals. More than 2 millennia ago, a device with intricate bronze gears as complex as an 18th century clock was lost in a shipwreck, a machine capable of predicting eclipses and the movements of heavenly bodies. For centuries, people living entirely in the northern hemisphere dismissed tales of sailors seeing the sun on their wrong side, a phenomenon that could only happen if they crossed the equator and ventured deep into the southern hemisphere. And deep in a Mesoamerican jungle, polished stones over 3,000 years old were found, stones that, if floated stubbornly, point towards magnetic north, hinting at a forgotten understanding of Earth's forces. These aren't just stories. They are puzzles from our past that continue to baffle experts today. Number 6. The Piri Reis Map's ghostly coastlines. In 1929, a discovery in the Topkapi Palace in Istanbul, Turkey, sent ripples through the worlds of cartography and history. A section of a world map, drawn on gazelle skin parchment in 1513 by an Ottoman admiral and cartographer named Piri Reis, was unearthed. What made this map so extraordinary wasn't just its age or its beauty, but the information it appeared to contain. Piri Reis himself noted on the map that he had compiled it from around 20 different source charts, including some contemporary Portuguese maps, maps allegedly captured from Christopher Columbus, and most intriguingly, maps drawn in the days of Alexander the Great. The map depicts the western coasts of Europe and North Africa, the coast of Brazil, and various Atlantic islands with a remarkable degree of accuracy for the early 16th century. This in itself was a significant find, shooting the advanced state of Ottoman cartography and their access to diverse geographical knowledge. However, it's the southernmost portion of the map that has fueled decades of debate and speculation. This section appears to show a landmass extending eastward from the southern tip of South America, a coastline that some observers, most notably Professor Charles H. Hapgood in the 1960s, controversially identified as a depiction of Queen Maud Land in Antarctica. The truly puzzling aspect is that Antarctica was not officially discovered until 1820 by European and American explorers. Furthermore, the landmass on Piri Reis's map is shown without an ice cap depicting coastline and possibly even inland features. Modern science, through ice core drilling and geological studies, indicates that the Antarctic continent has been covered by a massive ice sheet for millions of years, though there's ongoing research into localized ice-free periods much further back in geological time, or potential subglacial topography that might match. If the map indeed shows an ice-free Antarctic coast, the source information would have to be incredibly ancient, predating known human history by a vast margin, or it would require a period of significant deglaciation closer to our time that is not currently supported by mainstream scientific consensus. Piri Reis himself made no claim to have visited these lands or to have originated the information for the more mysterious parts of his map. He was a compiler, a scholar of the sea, gathering and synthesizing data from older sources. He explicitly stated that some of his source maps were of great antiquity. This leads to the question, what were these source maps? Could they have contained genuine geographical information passed down from a forgotten seafaring culture with advanced knowledge? Most mainstream cartographers and historians offer more conventional explanations. They suggest that the southern landmass is likely a distorted representation of the Patagonian coast of South America, perhaps bent eastward to fit the confines of the parchment or due to inaccuracies in the original source data. portolan charts, the type of navigational map Piri Reis, likely used as sources for coastlines, were excellent for depicting the Mediterranean and other known seas, but they struggled with large-scale geographical accuracy and often included speculative lands and unexplored regions. Projection used on the Piri Reis map, similar to portolan charts, also creates significant distortions, especially at higher latitudes, which could account for the unusual shape and orientation of the landmass in question. Some scholars argue that the supposed Antarctic coast is simply an imaginative filling in of an unknown area, a common practice among cartographers of the era when faced with blank spaces on their maps. The debate, however, continues. Experts have meticulously analyzed the toponyms, place names, and geographical features. While many locations in a known world are clearly identifiable, the names and features in the disputed southern region offer no easy answers. The map's accuracy in depicting the then recently explored coasts of South America is quite good, which makes the alleged gross distortion of its southern tip, if that's what it is, somewhat harder to explain for some. The puzzle is not just whether it's Antarctica, but how such detailed, seemingly accurate information, if it is accurate for any southern landmass, found its way onto a map in 1513 derived from sources that Piri Reis claimed were in some cases ancient even in his time. The Piri Reis Map remains a fascinating enigma, a cartographic whisper from the past that hints at lost knowledge or extraordinary unrecorded voyages, challenging our understanding of the history of exploration. Number 5. Viking sunstones. Navigating by invisible light. The Vikings, Norse seafarers who raided, traded, explored, and settled wide areas of Europe, Asia, and the North Atlantic islands from the late 8th to the mid-11th centuries, were renowned for their maritime prowess. They sailed vast distances across treacherous open oceans, reaching Iceland, Greenland, and even North America, Vinland, in their iconic longships. But how did they navigate? Especially in the high northern latitudes where fog is common, summer days can be perpetually overcast, and the pole star is too high in the sky to be a consistently useful guide for east-west travel. Magnetic compasses were not yet known in Europe during the Viking Age. Ancient Norse sagas, oral histories written down centuries later, contain intriguing clues. One such clue is the mention of a solarnine, or sunstone. In the saga of King Olaf, for instance, King Olaf is said to have used a sunstone to determine the sun's position on a snowy, overcast day. The saga describes him holding up the stone and observing where light emanated from it, thus revealing the sun's hidden location. For a long time, these references were dismissed by some as mere legend or poetic fancy. However, modern science and archaeological discoveries suggest there might be a factual basis to these tales. The leading candidate for the Viking sunstone is Iceland spar, a transparent variety of calcite. This crystal is abundant in Iceland and other parts of Scandinavia, and possesses a remarkable optical property called birefringence. When light passes through Iceland spar, it is split into two rays that are polarized differently. Polarization refers to the orientation of light waves. Skylight, even on a completely cloudy day, is polarized in a predictable pattern relative to the sun's position. By rotating a crystal like Iceland spar and observing how the two images it produces change in brightness or appearance, it's possible to detect this polarization pattern and thereby it's obscured by clouds or below the horizon, shortly after sunset or before sunrise. Numerous experiments conducted by scientists have demonstrated the viability of this technique. Using genuine Iceland spar crystals, researchers have been able to pinpoint the sun's bearing with an accuracy of just a few degrees, even under heavily overcast skies. The method involves looking through the crystal at the sky in the general direction of the sun and rotating it until the two images seen through it are equally bright or a specific pattern is observed. This orientation corresponds to the direction of polarization, which in turn reveals the sun's azimuth. Archaeological evidence, while not definitive, is suggestive. Crystals of Iceland's spar have been found in Viking Age graves and settlement sites. Perhaps the most compelling find is a piece of Iceland's spar, dubbed the Alderney crystal, discovered in the wreck of a 16th century Elizabethan ship off the coast of Alderney in the Channel Islands. While this ship post dates the Viking Age, it was found alongside other navigational instruments like dividers, suggesting that such crystals might have remained in use as navigational aids for centuries, possibly bridging a gap before more advanced instruments became common. Context of this find lends weight to the idea that these crystals were indeed part of a navigator's toolkit. However, the puzzle is far from solved. Direct archaeological proof of Vikings systematically using sunstones for navigation is still lacking. No sunstone has been found with clear markings, or in an undisputed navigational context, directly from a Viking ship. Skeptics argue that experienced Viking navigators would have relied on a range of other natural cues, such as wind, direction, wave patterns, the flight of birds, the color of the sea, distant cloud formations over land, and possibly even the migratory paths of whales. They contend that the saga references might be allegorical, or refer to something else entirely. Furthermore, the skill required to accurately interpret the subtle changes in light through a sunstone, especially on a pitching and rolling longship, would have been considerable, demanding extensive training and experience. Yet, the scientific principle is sound. The crystals were available, and the sagas provide tantalizing, if poetic, accounts. The idea of Viking mariners harnessing an invisible property of light to guide their voyages through the often sunless northern seas remains a powerful and intriguing possibility. Did these magical stones, as they might have seemed, truly help the Norse conquer the Atlantic? Or is this a case where modern science has found a plausible explanation for what remains, in historical terms, an unconfirmed practice? The sunstone continues to be a source of fascination, embodying the blend of myth, ingenuity, and mystery that surrounds Viking seafaring. Number 4. Olmec lodestones, America's first compass. The Olmec civilization, which flourished in the tropical lowlands of south-central Mexico from approximately 1400 BCE to 400 BCE, is often considered the mother culture of Mesoamerica. They are renowned for their colossal stone heads, sophisticated artwork, an early writing system, and their understanding of mathematics and astronomy, including the development of the Mesoamerican long count calendar. But among their lesser-known yet equally intriguing artifacts are small polished pieces of magnetic minerals that raise a profound question. Did the Olmecs understand and utilize the directive property of magnetism, potentially inventing a form of compass centuries, or even a millennium, before its first documented use in China? In the 1960s, during excavations at the major Olmec center of San Lorenzo Tenochtitlan, archaeologist Michael D. Coe unearthed a curious becket. It was a small, carefully shaped, and polished bar of hematite, a weakly magnetic iron ore. This papid, dating back to around 1400 to 1000 BC, was grooved, possibly to be suspended by a thread or to have a pointer attached. Subsequent experiments by Coe and others revealed something astonishing. If this hematite bar was floated on water, for example on a piece of cork or on mercury, which the Olmecs are known to have used, it would consistently align itself along a north-south axis. Specifically, it was found to point slightly west of true north, consistent with the magnetic declination, the difference between true north and magnetic north, in that region at that time, if it were indeed orienting to magnetic north. This discovery was not an isolated one. Similar artifacts, often bar-shaped and made from various magnetic minerals like magnetite, lodestone, a naturally magnetic iron ore, or other forms of hematite, had been found at other Olmec and pre-Olmec sites, such as Izapa. Some of these objects are meticulously crafted with sighting lines, notches, or perforations, suggesting a deliberate and purposeful design. Care taken in their manufacture implies they were not mere trinkets, but objects of some significance. The implications are significant because the earliest known use of a magnetic compass comes from Han Dynasty, China, around the 2nd century BCE to 1st century CE. Initially, these Chinese devices, often lodestone spoons that rotated on a smooth diviner's board, were used for geomancy and divination, not navigation. The use of the compass for maritime navigation in China is documented much later, around the 11th or 12th century CE, and it reached Europe sometime thereafter. If the Olmec artifacts were indeed used as direction-finding devices, it would mean that the discovery of the directive property of magnetism occurred in the Americas independently and much earlier than in the Old World. However, the precise purpose of these Olmec artifacts remains a subject of debate among experts, primarily because the Olmecs left behind no written records that explicitly describe their use. Several hypotheses have been proposed. One is that they were indeed primitive compasses, used for orientation in travel or for aligning ceremonial structures. Many Olmec ceremonial centers, including La Venta and San Lorenzo, are laid out along axes that are consistently offset from true north by about 8 degrees west of north. Some researchers have suggested that these alignments might correspond to magnetic north during the period of their construction, or perhaps to significant astronomical risings or settings, such as those of certain stars or the sun at solstices. A magnetic device could have aided in achieving such precise alignments for their monumental architecture. Another possibility is that these magnetic artifacts were used for ritualistic or divinatory purposes. The ability of a stone to mysteriously orient itself would undoubtedly have been seen as a powerful, perhaps supernatural phenomenon in Olmec society. They might have been employed by shamans or priests in ceremonies similar to the early Chinese use of lodestone spoons for divination. The intricate workmanship on some pieces certainly suggests they were objects of value and possibly spiritual importance. Skeptics point to the lack of conclusive evidence for their use as navigational or surveying tools, while the artifacts do align magnetically, proving this was their intended function, and that the Olmecs understood the principle is challenging without direct textual or iconographic corroboration. It's also possible their magnetic properties were coincidental or recognized, but applied in ways we haven't yet fathomed. Yet, the San Lorenzo hematite bar, sometimes referred to as a geomagnetic compass pointer, remains a compelling piece of evidence. Its age, its careful shaping, and its demonstrable magnetic properties present a tantalizing puzzle. Could this ancient Mesoamerican civilization, which achieved so much in art, architecture, and calendrics, have also unlocked one of the fundamental forces of nature, using it for purposes that are now lost to time? The Olmec lodestones whisper of a technological sophistication that continues to challenge our understanding of the ancient Americas. Number 3. The Phoenicians' epic African voyage. The Phoenicians, originating from the coastal cities of the Levant, modern-day Lebanon, Syria, and Israel, were the preeminent mariners of the ancient Mediterranean world. From around 1500 BCE to 300 BCE, their ships, famed for their sturdiness and sailing qualities, dominated maritime trade, establishing colonies and trading posts from Cyprus to Spain, and even venturing into the Atlantic. While their exploits within the Mediterranean are well documented, one account, if true, describes a voyage of such astonishing scale and daring that it continues to puzzle historians and archaeologists. The alleged circumnavigation of Africa, around 600 BC. Our primary source for this incredible claim comes from the Greek historian Herodotus, often called the father of history, who wrote his histories in the 5th century BC, about 150 years after the supposed event. According to Herodotus, The Egyptian pharaoh Necho II, who reigned 610 to 595 BCE, was keen to determine the extent of Libya, the ancient Greek term for the African continent. To this end, he commissioned a fleet of Phoenician sailors, renowned for their seamanship, to undertake the monumental task. Herodotus states that Necho II ordered the Phoenicians to set sail from a port on the Red Sea, proceed southward along the eastern coast of Africa, and, if possible, round the continent's southern tip and return to Egypt via the Pillars of Hercules, the Strait of Gibraltar, and the Mediterranean. The voyage, as recounted, was an epic undertaking that lasted 3 years. The Phoenicians reportedly sailed south, and each autumn when the season was right they would go ashore, sow a patch of ground with grain, wait for the harvest, and then, having reprovisioned themselves, put to sea again. After 2 years of this pattern, Herodotus says, they passed through the Pillars of Hercules in the 3rd year and arrived back in Egypt. The most striking, and for many scholars the most convincing detail in Herodotus's account is one that Herodotus himself expresses skepticism about. He writes, "These men made a statement which I do not myself believe, though others may, that in sailing round Libya they had the sun on their right hand." For Herodotus, and indeed for anyone living in the northern hemisphere, the sun at midday is always in the southern part of the sky. To have the sun on one's right-hand side while sailing westward would mean the sun was to the north. This phenomenon is precisely what would occur if a vessel crossed the equator, sailed around the southern tip of Africa, which lies well south of the Tropic of Capricorn, and then proceeded westward along the southern coast of the continent. The fact that Herodotus, unfamiliar with the celestial mechanics of the southern hemisphere, reported this detail while doubting it, lends a strong ring of authenticity to the story for modern interpreters. It's a detail unlikely to have been invented. If the voyage did occur, it was an achievement of staggering proportions for its time. The journey would have covered an estimated 15,000 to 17,000 miles through waters entirely unknown to Mediterranean sailors. They would have faced diverse and challenging maritime conditions, from the monsoon winds of the Indian Ocean to the powerful currents and storms of the South Atlantic. Navigation would have been a constant challenge. Lacking magnetic compasses, the Phoenicians would have relied on coastal piloting observations of the sun and stars, which would appear to behave differently as they moved south, understanding prevailing winds and currents, and presumably information gathered from any coastal communities they encountered. The logistical hurdles would have been immense. Supplying a fleet for a multi-year expedition, maintaining the seaworthiness of their ships in remote waters, and managing relations with potentially hostile or unfamiliar indigenous populations along the African coast crowds. The strategy of landing and cultivating crops each year, as described by Herodotus, seems a plausible, if slow, way to sustain such a long voyage. Naturally, there is considerable skepticism. Some historians doubt the feasibility of such an extended voyage with the shipbuilding and navigational technology available to the Phoenicians. They point out the lack of corroborating archaeological evidence, such as Phoenician artifacts or inscriptions found along the sub-equatorial African coastline, that would definitively prove such a passage, though such evidence is notoriously difficult to find and preserve over millennia. Herodotus was, after all, reporting a story he had heard, not a first-hand account. Could it have been an exaggerated tale, or a misunderstanding of a more limited exploratory voyage? It is known that Hanno the navigator, a Carthaginian, Carthage being a powerful Phoenician colony in North Africa, undertook a significant exploration of the West African coast around 500 BC, possibly reaching as far south as Sierra Leone or even Gabon. A Greek translation of his account, known as the Periplus of Hanno, survives. This confirms the Phoenicians' capability for long-range Atlantic voyages, but it was not a full circumnavigation. The puzzle of Necho II's Phoenician expedition remains. Did these ancient mariners truly achieve a feat that would not be definitively surpassed for another 2 millennia until Vasco da Gama rounded the Cape of Good Hope in 1498? Though he sailed in the opposite direction and his initial voyage was not a full circumnavigation, is the very detail that Herodotus found unbelievable the key to unlocking the truth of this extraordinary ancient voyage. The story stands as a testament to the potential daring and skill of Phoenician seafarers, leaving us to wonder about the true limits of exploration in the ancient world. Number 2. The Antikythera mechanism. Ancient Anagar computer. In the year 1900, sponge divers off the coast of the Greek island of Antikythera, nestled between Crete and the Peloponnese, stumbled upon an ancient Roman-era shipwreck. Among the treasures recovered from the seabed over the following months, statues, pottery, glassware, and coins, was a heavily corroded and encrusted lump of bronze. Initially overlooked, this unassuming object, which had fragmented into several pieces, would eventually reveal itself to be one of the most perplexing and sophisticated Nechnasogolate artifacts ever discovered from the ancient world, the Antikythera mechanism. Dating from sometime between 205 BC and 60 BCE, the device, once cleaned and studied, began to unveil its secrets. It was not a weapon, nor a piece of art, but a highly complex mechanical calculator. Housed originally in a wooden box roughly the size of a shoebox, about 34 cm high, 18 cm wide, and 9 cm deep, the mechanism consisted of an intricate assembly of at least 30, and possibly as many as 72, interlocking bronze gears of various sizes. The front and back faces of the box were covered in dials and pointers, and extensive Greek inscriptions provided a sort of user manual. Decades of painstaking research, involving advanced techniques like X-ray computed tomography and high-resolution surface imaging, have allowed scientists to reconstruct much of its internal workings and understand its functions. The Antikythera mechanism was in essence an analog astronomical computer. By turning a hand crank, now lost, the user could set the mechanism to a specific date, and its various pointers would indicate a wealth of celestial information. Could predict the position of the sun and the moon and the zodiac with remarkable accuracy. It modeled the moon's variable motion through the sky, incorporating the ancient Greek understanding of its elliptical orbit, likely based on Hipparchus's theory of epicycles, using a clever pin and slot mechanism that mimicked this irregular movement, a feature known as differential gearing, which is astonishingly advanced for its time. Furthermore, the mechanism could predict solar and lunar eclipses based on the Saros cycle, an approximately 18-year, 11-day, 8-hour period, after which eclipses tend to repeat. It also displayed the phases of the moon. On its back dials, it incorporated calendars, including the Metonic cycle, a 19-year cycle that reconciles solar years and lunar months crucial for luni-solar calendars, and the Callipic cycle, a 76-year refinement of the Metonic cycle. It even had a dial that indicated the timing of the Pan-Hellenic Games, such as the Olympic, Pythian, Isthmian, and Nemean Games, highlighting its cultural as well as scientific significance. The sheer complexity of the Antikythera mechanism is what makes it so puzzling. Nothing comparable in terms of sophisticated gearing and mechanical engineering is known to have existed in Europe until the astronomical clocks of the 14th century CE, over 1,000 years later. Its existence challenges many preconceived notions about the technological capabilities of the ancient Greeks. Where did such knowledge come from? Was this device a unique singular marvel created by a lone genius? Or is it the sole surviving example of a forgotten tradition of complex mechanics? The origin of the mechanism is still debated, though Rhodes, a center of Greek astronomy and engineering, home to the astronomer Hipparchus and the polymath Posidonius, or Syracuse, home of Archimedes, who was renowned for his mechanical ingenuity, including a purported sphere that modeled celestial motions, are often cited as possible places of manufacture. While the Antikythera mechanism was not a direct navigational tool in the sense of a compass or a sextant, its implications for ancient navigation are profound. Precise astronomical knowledge is fundamental to navigation, especially for determining latitude at sea and for understanding celestial cycles that could influence long-term voyage planning. Could the mechanism, or similar devices, have been used to generate astronomical tables for navigators? Or did the underlying mechanical expertise and understanding of gearing principles find application in other, now lost, navigational instruments? The device demonstrates a level of theoretical understanding and practical craftsmanship that was previously thought to be far beyond the reach of that era. The greatest puzzle surrounding the Antikythera mechanism is its apparent isolation. If the Greeks were capable of building such a device in the 2nd or 1st century BCE, what happened to this tradition of advanced mechanics? Why does there appear to be such a long gap in technological development before similar complexity re-emerges in the late Middle Ages? Did this knowledge simply die out? Or was it preserved in ways we have yet to discover? The Antikythera mechanism serves as a stunning reminder that our ancestors may have possessed far more sophisticated knowledge and technological prowess than they are often credited for. It is a fragment of a lost world of ingenuity, an ancient computer that still whispers of untold technological achievements from over 2 millennia ago, hinting that what we know of ancient technology might just be the tip of a much larger submerged iceberg. Number 1. Polynesian wayfinding, masters of the ocean wilderness. The settlement of the vast Pacific Ocean by Polynesian navigators stands as one of the most remarkable achievements in human history. Over a period spanning millennia, with a major wave of long-distance voyages occurring roughly between 700 CE and 1400 CE, these intrepid seafarers set out from Southeast Asia and Melanesia and their double-hulled and outrigger canoes, exploring and colonizing an Inori-Kanagal of ocean. This area stretches from Hawaii in the north to Aotearoa, New Zealand, in the southwest, and to Rapa Nui, Easter Island, in the southeast, encompassing tens of millions of square miles of water and thousands of islands, many of them mere specks in the immense ocean. The central puzzle that has long captivated researchers is how these ancient mariners, without the aid of magnetic compasses, sextants, chronometers, or written charts as we understand them, were able to navigate with such extraordinary precision across thousands of miles of open sea to find and settle these tiny, often isolated landfalls. Their success was not accidental. It was the result of a deeply sophisticated and holistic system of knowledge passed down through generations. Polynesian wayfinding was not reliant on a single technique, but was a complex tapestry woven from meticulous observation of the natural world. One of the foundational elements was a highly developed star compass. Navigators memorized the precise rising and setting points of hundreds of stars and constellations on the horizon. These memorized points effectively created a 360-degree compass, allowing them to maintain a consistent heading day and night. As one guiding star rose too high or set, the navigator would vacantly switch to another star that rose or set on the desired bearing, or adjust their course based on the known paths of successive stars. The sun's path across the sky during the day, its position at sunrise, noon, and sunset, and its seasonal shifts and declination was also a crucial directional guide. The moon's phases and its path were similarly integrated into their mental maps of the cosmos. Perhaps the most subtle and astonishing aspect of Polynesian navigation was their profound understanding of ocean swells and wave patterns. They could identify and interpret multiple distinct swells simultaneously moving through their canoes. These long-period ocean swells are generated by distant storm systems and can travel for thousands of miles across the ocean, maintaining a consistent direction. Experienced navigators could feel these subtle motions through the hull of their canoe, even in complete darkness or when the sky was overcast, using their own bodies as sensitive instruments. More remarkably, they understood how these swells interacted with land. As swells approach an island, they refract, bend around it, and reflect off it. This creates characteristic interference patterns in the water, a shadow or echo of the island in the waves, that a skilled navigator could detect from many miles away long before the island itself was visible. They knew how to read the zone of confused seas that signaled the presence of land, disrupting the regular rhythm of the ocean swells. To aid in teaching and memorizing this complex knowledge of swell patterns and island locations, Micronesian navigators whose techniques share common Austronesian roots with Polynesians developed stick charts. These were not charts taken on voyages, but rather pedagogical and mnemonic tools used on land. There were different types. Matang charts illustrated general principles of how swells interact with an island. Rebellable charts depicted the actual locations of islands within an archipelago and the prevailing swell patterns connecting them, and meadow charts focused on a specific island or a small group, showing more detailed information about wave patterns in its vicinity. In these charts, curved sticks represented swell lines, and cowrie shells or small pieces of coral marked the positions of islands. Beyond stars and swells, Polynesian navigators utilized a wealth of other environmental cues. They observed the patterns of clouds. Certain types of cumulus clouds tend to form over islands due to rising warm air, and the greenish tint on the underside of a cloud could indicate light reflected from a shallow lagoon. Stationary clouds in a sky where other clouds were moving with the wind could also betray the presence of land. The flight paths of land roosting seabirds were critical indicators. Birds flying out to sea at dawn to feed and returning to their island roosts at dusk provided a direct line to land, especially when an island was close, but still out of sight. Changes in water color. The presence of land-derived debris like floating vegetation, specific types of fish or marine life associated with shallower waters or reefs, and even subtle changes in water temperature or salinity could all provide clues to a keen observer. This immense body of knowledge was not written down, but was transmitted orally from master navigators, such as the Palu in the Caroline Islands of Micronesia or the Tahona in Polynesia, to their apprentices through years of rearience at sea. Cognitive demands of memorizing and integrating this vast array of information were immense. The efficacy of these traditional methods was dramatically demonstrated starting in the 1970s with the voyages of the Hokulea, a replica of a traditional Polynesian voyaging canoe. Guided by master navigators like Mau Pialug from Satawal in Micronesia, and later by his Hawaiian student, Nainoa Thompson, Hokulea successfully completed numerous long-distance voyages across the Pacific, including trips to Tahiti, Aotearoa, Rapa Nui, and even a circumnavigation of the globe using only traditional wayfinding techniques. These voyages proved beyond doubt that the ancient methods were not only viable but incredibly effective. Despite these modern replications and our growing understanding, the full depth of Polynesian wayfinding still holds an element of mystery. The sheer sensory acuity required the ability to perceive and interpret such subtle environmental cues amidst the vastness of the ocean, and the unwavering confidence to sail into the unknown for weeks or months on end, are awe-inspiring. How this intricate system was first developed, refined through countless trials and errors across such enormous and perilous distances, allowing for the deliberate settlement of 1/3 of the Earth's surface, remains a profound testament to human ingenuity, courage, and an intimate, almost symbiotic relationship with the natural world. Polynesian navigators were true masters of the ocean wilderness, reading the language of the sea and stars in ways we are only beginning to fully appreciate.